Hi everyone, welcome back to your second lecture in Astronomy 103 here in the summer of 2018. I hope you're getting used to the format of the class. I know that there's rather a lot to do every week. Remember that everything is due by the Sunday of that week by midnight. So you want to try to get everything done. I would not leave it all till Sunday. I know that some of you are working and have other things that you're doing. Try to do a little bit every day so that you don't fall too far behind. Okay, so let's get started. So we're still in chapter 1, and in today's lecture we will get through the first part of chapter 2 as well. Again, I recommend that you read the book before you listen to the chapters or look at the lectures, certainly before you do any of the quizzes, etc. So please make sure you're paying a lot of attention to your book. Okay, so today we're really going to talk about science, just in general, because it's one of those things that, of course, you hear about many times, things like the scientific method. You've probably heard about that since grade school. But we're going to try to be a little bit more specific about what is science, what isn't science, etc. All right, well, just to point out, and I know you all know this, but science is really born out of curiosity, right? So you know, if you're curious about something these days, you just Google it, but in some sense you're being a scientist, right? You're going out and trying to find out something about something you're interested in. Um, and you know, what if Google doesn't have an answer for you, right? Well, that's where you actually have to figure out how to understand something yourself. Maybe an experiment needs to be done. Maybe data needs to be collected about whatever you want to know about. So, you know, this has been a characteristic of humans forever, right, since we've been around. And an interesting example I've always liked is this example they give in the book and shown here in the pictures. Um, is, you know, using plants and animals to make dyes for clothing. So you can imagine when people were first making clothing, it was, as far as we know, a lot of animal furs, animal skins were used to make clothing. But as we progressed in culture, um, people really wanted to have color in their clothes, and that was kind of hard to come by. So people did a lot of work. You know, if they would see something in the natural world with a beautiful color, to take that color and try to make an actual dye. And something like indigo is one of the oldest dyes that we know that people have made from plants and animals, um, and been able to actually use that to dye clothing, and we still use this today. Obviously, we have lots of dyes that are available today, but indigo is one of the oldest ones. And so, really, this idea of being curious about something, what makes this flower a particular color, and then figuring out the chemistry that you need to do to extract that dye, is very much science. You might think of that as more like applied science, right? Uh, but that distinction is something that we really only use today, right? So, in previous years, you know, 100 years ago, those two things were really meshed together. So people, maybe more like 150 years ago, it was much more common to have this application and discovery be sort of a meshed idea. Today we think about, you know, there's theorists who are, you know, thinking about stuff, right, doing a bunch of math, let's say in physics, and then there's experimentalists who test it out. But you know, it used to be that you kind of do both when you were a scientist 150, 200 years ago and before. Now, of course, as we talked about before, humans have been very interested in patterns in the heavens, right? So if they look up and see stars, they certainly would see patterns. They would see planets, which would be not fixed in the sky, right? They moved around. Of course, they saw the moon, which had phases and all kinds of things. And looking for patterns in those celestial objects is really, you know, something that was could have been used for predicting the weather or predicting the seasons at least. So this was very useful, and etc. The idea is just that humans observe and learn. It's what we do, right? So let's think about how you actually would go about doing this if you're a scientist. There is something called the scientific method. Again, like I said, you've probably learned about this in grade school. So let's think about it. So this is sort of a process. Now, the process doesn't always exactly go this way. We'll talk about that in a second. But, in an ideal world, this is what would happen. You'd see something in the natural world. That's the observation. Then you would think about, well, what could have caused that thing I just saw, right? So you see some phenomena. Then you say, well, what could have caused it? And then you make a hypothesis about what could have caused it. And then you conduct experiments, and you might find out that your idea about what caused this thing that you observed were not correct. And if that's the case, then you fail to confirm that hypothesis, and now you got to go back to the drawing board, start all over again, and figure out another idea for what might have caused this thing that you observed. Of course, you could have been right, and you confirm, and once you confirm a hypothesis, it's very important that what you have to do now is go out and make more observations, right? And hopefully you can control this hypothesis, meaning you can set up an experiment where you've controlled you've controlled this cause, and then you make new observations, new predictions, and go look out in the world for how all of this works. And again, science is not a bunch of facts, although there are a lot of facts in a particular field in science, but that's not really what it's about. It's about this idea of discovery, putting through a hypothesis, testing the hypothesis over and over and over again. Now, scientific advances, how do they happen? Well, sometimes it's because somebody followed that outline I just showed you and saw something, made a hypothesis, did the test. That's great when that happens, but sometimes it doesn't happen that way. So first of all, I'm going to go back and talk about the scientific method again, showing you a little video about the scientific method, and then we'll talk about times when a very famous time in which the scientific method was not the way the discovery was made. So let's take a look at this video.
House cats are good at a few things, mostly sleeping, destroying things, and starring in countless hours of online videos. But can they swim? We probably all have an opinion on this important question, and some of us, unfortunately, have directly experienced a cat coming into contact with water. For a scientist, however, such questions are best answered by applying what is known as the scientific method. The first step in the method is to propose a correct answer, which is also the most cautious one. Cats cannot swim. This is called the null hypothesis. Null means nothing, or zero. The next step is to collect evidence in a systematic way to test the hypothesis. We can either reject the null hypothesis or fail to reject it. Yes, this is a negation of a negation, but remember, scientists are cautious. The simplest way to test whether cats can swim would be to toss about 100 of them, one at a time and on separate occasions, into a pool of water. Of course, if any of the cats failed to swim, we'd rescue them before they came to any harm. Anything less would be unethical. Fortunately for science, the internet hosts a lot of videos about cats, more than 1 million on YouTube alone, and it looks like some cats actually can swim. However, if you divide the number of swimming cat videos by all the cat videos on YouTube, you see them swimming in less than 1%. In any case, we now have multiple pieces of data, videos of cats swimming in deep water, to provide evidence in support of rejecting the null hypothesis. Does this mean that cats can definitely swim? After all, those videos could have been faked. Direct and humane observation of many cats may be the best way to answer this question. So, we suggest, if you really want to know if cats can swim, you spend as much time as possible watching them amble, paddle, and sleep their way through their days. For Scientific American's Instant Egghead, I'm Yasmin Tayeb.
Okay, so in that video, right, what she was talking about, let's go back to this slide real quick, that whole idea of the null hypothesis. It's really what she was saying is that when you propose an answer to a question, if you have a question, can cats swim, that you should be cautious, right? You shouldn't say, yes, of course they could swim. That's my hypothesis. Now, sure, you could do that, and then you can go test it, and then you may or may not find out it's true. But again, scientists try to make the most cautious hypothesis they can, and that would be cats can't swim, and then go and do experiments. And the point being made in that video really is that yes, you can watch YouTube videos and you'll probably see some swimming cats, but there's not very many of those compared to all the cat videos there are. So really, you need to do the experiment. Right. Well, whether someone's going to do that experiment or not, and of course, humanely. Um, to really understand that direct experiment is something that scientists strive for. Sometimes that's not possible, right? It's just not possible to do, and you got to figure out another way to test something. So again, it's great when this kind of thing works out and you can make an observation or ask a question, make a hypothesis and do the experiment and everything works out. But sometimes that's not how science proceeds. And if we look here, this is Fleming, who discovered penicillin, and the way he discovered penicillin is very interesting because it's totally not the scientific method, and it's very fortuitous that it was discovered in the first place because I'm sure you know, but before he discovered penicillin, there were really no antibiotics. There was something called sulfa, which is still used today actually. It does have antimicrobial properties. It's just not an antibiotic. It did sort of work against some bacteria in some kinds of infections, but really not very effective. And millions of people died every year from just simple bacterial infections. You cut your toe, it get infected, and you would die. Things like tuberculosis were, fatal. So it was a very big deal for antibiotics to be discovered. It saved a whole lot of lives. And now we're in the situation where they don't work as well as they used to because the bacteria are learning to be resistant to these antibiotics. And that's a very dangerous situation. So I hope that everybody listening to this takes it seriously when your doctor says finish all of your antibiotics, because if you don't, the bacteria that are still in your body can learn to be resistant to that antibiotic, and then you've got a really big problem. And the other thing is, you don't use antibiotics when you don't need them. You have to be very cautious. When I was a kid, you got even a slight sore throat. They didn't even test you for strep. They just gave you a big shot of penicillin. And people don't do that anymore because it's very bad. It really can cause the bacteria to become resistant quite quickly. Anyway, that's my little tirade on antibiotics. Let's look at a video about this discovery. Lucky for us. Let's see. Gotta get out of full screen. Hold on a second. All right. Here we go. Let's make this guy full screen.
Alexander Fleming was a Scottish biologist and pharmacologist, best known for his discovery of the antibiotic penicillin. Fleming actually discovered penicillin on accident. He had been studying a bacteria called Staphylococcus and left a petri dish of bacteria on a bench near an open window when he left on a vacation with his family. When he came home, he saw that some mold had blown in from the open window and landed on the bacteria in the petri dish. This mold had killed all the bacteria around it. He realized that the mold was killing bacteria that caused diseases like pneumonia, scarlet fever, meningitis, and diphtheria. This mold was the discovery of penicillin. During World War II, there was a huge need for penicillin. With all the soldiers being wounded in the war, large amounts of penicillin were needed to treat their infections. But no one knew how to produce large quantities of it. Andrew Moyer discovered a way to grow big batches of the mold used in producing penicillin, making it possible to produce enough penicillin to treat all the soldiers who needed the drug. Moyer's discovery saved many people's lives then and now. The discovery of penicillin won Alexander Fleming the Nobel Prize in 1945.
Yeah, kind of amazing. And so, I think, of course, this is a very fortuitous thing that happened, mold blowing in through the window, landing on a petri dish. But think about it, when he came back from vacation, he saw this, he didn't just toss it, right? He could have been like, I ruined my petri dish of bacteria, I'm going to toss it out. I mean, he, as a scientist, was curious. Why were all this, this weird mold that came in, why were all the bacteria dead? So this is something that, again, this the scientific idea of curiosity, and All of us have curiosity, which means that in some sense, all of us are scientists. By the way, fun fact, the same mold that is used to make penicillin appears in blue cheese. Penicillium mold. It is used to make all the blue deliciousness of a blue cheese. Now, I know probably some of you don't like blue cheese. It's one of my favorites. And the interesting fact is that some people who are allergic to penicillin can eat blue cheese and some people can't. So some people are sensitive enough to that mold that they can't eat blue cheese. Anyway, fun fact. Okay, so let's go back to our slides. All right. So again, scientific advances, they don't always happen the way that you get taught about the scientific method. It just sometimes doesn't happen that way. A lot of times too, you don't make that hypothesis. You're sort of exploring. You're looking at data, taking data, looking at it, and trying to figure out, are there patterns in that data that would lead to a hypothesis or lead to some new understanding. So very often this scientific method that we tout a lot in school is not really the way science gets done. But at some point it has to be very systematic, right? It has to be about an experiment. And Fleming, after he discovered that this mold had killed all the bacteria, did experiments to see if that was actually true, right? So he didn't just like, oh, I've discovered something and then they started producing penicillin. He had to do a bunch of experiments to make sure that that's what he really thought happened. It wasn't some other thing that killed the bacteria. So at some point you have to be very systematic in your scientific thinking. Okay, so again, I put these slides here just to show you sort of a breakdown of the ideal scientific method. I'll just put these here for you to look at later. We're not going to go through them because we've spent a bunch of time on this, but just so you know, they're here. Okay, now again, if your data doesn't support your hypothesis, you got to go back and first thing you should always do, check your experimental design and setup for errors. Maybe you screwed up. You did an experiment and you did it wrong, right? So that is the first thing that all scientists do, and sometimes it takes them a very long time to check this and make sure that to either find an error that they did make or make sure there wasn't an error. When we talk about the cosmic microwave background that was discovered by a antenna, basically, it's kind of a little bit of a radio telescope, really early radio telescope. When they first saw this signal they were getting from this background radiation, they really had no idea. They thought it was an error. They thought there was something wrong with their instrument. And they did at least a year, I think it was a little bit more than a year, of checking that equipment over and over again, trying to figure out what could be causing this. And finally, they took every single idea for what could be the error and then cross it off their list by doing experiments and by trying to figure out where those sources could be, and finally realized that there was a real signal. So that checking for errors is very important. Again, let's say that you figured out that your thing didn't have any error, your experiment has no errors. You have to recheck your hypothesis and your original observations. So many things go into finally figuring out, did you do this right? Is what you're seeing real in your experiments? We'll talk about that more as we go through things like the cosmic microwave background experiments. All right, so this is something, scientific theory, that is often misused in the sort of when people talk about science and they talk about theories, they often have a misunderstanding of what a theory is. So the way that we use the word theory in everyday life is really very different from how a scientist uses the word theory. So if you think about when you say, well, I have a theory about why my car won't start, you're really talking about a hypothesis, right? Because it's an idea about why your car doesn't start. You observed your car doesn't start, and you're like, okay, I have a theory about that. My alternator's bad, right? And then you got to go and figure out what tests to do. Maybe you just take it to a mechanic. But if you're handy with cars, you might go do your own test to figure out if it's the alternator, or it's the battery, or it's something else, right? So you often use the word theory when you really mean hypothesis, because it's a guess about why your car won't start. But you don't ever hear anyone say that, right? I mean, maybe here and there, but you don't usually hear them say that in sort of everyday life. The way we speak in everyday life, we don't use the word hypothesis that way. We use the word theory. However, in science, a theory is not a guess, it's not a hypothesis. It is an explanation for something that has been tested over and over and over and over again. So we don't call something a theory until it explains some natural phenomena and it's been tested over and over and over again. So think about the theory of gravity, right? Now, obviously, you probably think of gravity as being something that you just accept as true, right? That it's a fact. Well, really, a scientist that thinks of that as a theory because it explains things like when you drop something, it falls. It explains things like the Earth going around the sun and the moon going around the Earth, right? But it has been tested over and over and over again in actual scientific experiments, not just observations, but experiments, and has come out to be true, right? Now, people are still testing the theory of gravity. That's how scientific theories work. You're never done, like never, ever done. There's a satellite up orbiting Earth that's called Gravity Probe B, and it's there to test gravity again. So we test a theory over and over and over and over again in every possible way you can think of. So that's kind of a very different thing than a hypothesis, which is a guess for why something is happening. So when people say, something's just a theory, and I've heard things, people say, well, evolution is just a theory. Well, that's absolutely not correct because what they mean to say is evolution is just a hypothesis, which is untrue. It has risen to the status of theory, which means it has been tested over and over and over again and explains natural phenomena, just like the theory of gravity. So that's very important to understand because, of course, there's all kinds of debate that happens from the misunderstanding of what a scientific theory is. All right, so on that note, let's talk about pseudoscience. So what is pseudoscience? Well, it's any claim, belief, or practice that's presented as scientific, like, for instance, how the planets are aligned somehow affects your daily life. Okay, that's kind of sounds a little scientific, doesn't it? Somehow the planets are affecting you, your biology or your mind or whatever it is, to change the way you're going to behave on this particular day, or change the personality that you were born with somehow. That kind of sounds a little scientific, doesn't it? But there's no test of this, right? It hasn't passed any tests. So when people have tried to test that, it doesn't pass at all. So one way you could test it, right, is you could see if you put, let's say, I'm sure some of you have read your horoscopes. So if you take a horoscope and you give everybody the same horoscope, right, don't tell them you're giving them the same horoscope, and ask them how that matches with their actual whatever happened that day. So a lot of times these are daily horoscopes you can read in the paper, etc. You could give everybody the same one, not tell them, and then ask them how it matches with, say, the previous day. And what ends up happening when you do that experiment, it's fun to try with your friends, is that a lot of them say it does match because these things are written to be very general, to really match with most people, and people sort of read stuff into the lines that is relevant to them. Anyway, so there's, of course, lots of tests that people have done to see if astrology is actually meaningful at all, and it really isn't. So pseudoscience is something that you see a lot in the world, and it comes in all kinds of different things, like, supplements that claim to do a particular thing and have not ever been tested. That can actually be dangerous, by the way. And so it's something to watch out for. A lot of times it's presented, especially now with the advent of the web, as being very scientific, and it's not. So you have to know how to sort of suss out pseudoscience, again, because it can be dangerous if you're, say, taking a supplement or something without any evidence that it is not harmful. Anyway, okay, so what science is and is not? Well, scientific discovery usually results from rigorous testing of something, right? there's experiments, there's repeatability. So somebody goes, does a bunch of experiments, finds a particular result, and then a different whole group of scientists repeat that to make sure it's true. Now, sometimes they don't find that it is true, and then that particular thing that was found was not true. And in physics, usually nobody accepts anything as being true, in astronomy as well, until it's been replicated by many different laboratories, many different scientists. And in pseudoscience, something like astrology makes claims that lack any evidence or even plausibility, right? So you have to sort of be able to suss that out. Okay, so let's try a question. And remember that what you're going to need to do on this next slide is pause the video, and I'll tell you when. So just make sure to read all this. You're trying to figure out, is it a pseudoscience or is it a science? So pause the video now and answer the question.